Mathematica has some really useful functions for investigating the behavior of mathematical and physical expressions, and I want to show you one called manipulate that I use very, very frequently. I'm going to show you the plot of a function, and then after I show you the plot of the function, I'm going to go into how I can vary parameters in the function and see what that function does as I vary those parameters. So watch this all the way through. I'm starting off with some steps that you may already know. First thing I'm going to do is clear everything in the notebook. And then I'm going to, what I'm going to use as the model for working with here is this circuit, which many of you may recognize as the RLC bandpass filter. And you don't need to know that, just know that there is a relationship for the gain of this, voltage gain of this circuit that depends on a number of different parameters: the frequency of the source, the resistance, the capacitance, and the inductance of the components. And so we're going to investigate that relationship. I'll introduce you to that relationship, and then we'll see how we're going to investigate its behavior. So in this circuit, it depends on the inductance and the capacitance and the resistance, and so I'm going to start with some selected values. Maybe I've got this set up on a breadboard with these component values for the inductance, capacitance, and resistance. You notice that I use double capital letters for these. There are some capital letters that are defined constants or defined functions in Mathematica, and to avoid that, I frequently double the definitions of variables if I'm using capital letters to make sure I'm not using one of the defined constants. You also know that I'm using Mathematica commenting in order to indicate to me what these quantities are and their units, and that's a really important step when you're working with physical systems. Okay, so here is the function that describes the voltage gain of that circuit. You see, in this function, it does depend on the frequency of the function generator. It depends on the inductance, resistance, and capacitance of the components. And I am going to plot this using the component values that I defined above, the inductance, capacitance, and resistance that I defined above. We'll go ahead and plot this as a function of frequency. You will notice that I'm going to do the plot for a frequency range of 100 hertz to 30,000 hertz. I've picked that out. And when I ask Mathematica to do the plot, I want the x-axis to run from 100 to 30,000, and I want the y-axis to run from 0 to 1. So that's the plot range that I'm going to select. Of course, you don't need to use this plot range. It's optional, but sometimes Mathematica chooses a plot range, if you don't give it, that may not show you the entire plot. And that would be the case here. It wouldn't show me the entire relationship, and I want to see the entire relationship, so I've defined this plot range. Okay, so let's see what the plot looks like. And here is the gain relationship, voltage gain relationship for that LRC circuit. Now, what I might want to do is I might want to say, okay, I wonder what that gain relationship looks like if I vary the capacitance. That might be one of the things I want to do. And so the next thing I'm going to do is I'm going to say, okay, let's suppose I had a capacitance that is CC1, a different capacitance that is different from the original capacitance CC. So we'll make it 7.5 times 10 to the minus 9 farads as opposed to 10 times 10 to the minus 9 farads. And you see in my new plot relationship, I'm going to plot both the old relationship with L, R, and C that were originally defined, and I'm going to plot a second relationship with L, R, and CC1. And this is the way that I tell Mathematica to make a plot that has two different relationships in it so that I can compare those relationships. I'm going to let the frequency have the same range. I'm going to have the X and Y axes cover the same range for both of these plots, and you will see when I execute this that both plots will show up when I execute it. So the blue plot here is the original relationship with L, R, and C, and the gold plot is the relationship with my new value of CC1 inserted in there. So I can now see, okay, this is the effect that changing the capacitance has. Now I could go through with these plots and say, okay, I wonder what happens when I change the resistance. I wonder what happens when I increase the capacitance. I wonder what happens when I decrease the inductance. What if I decrease the inductance and increase the resistance? What would that do? Okay, so here's where it gets really interesting. There is a manipulate command in Mathematica that allows me to ask exactly that question. So once again, I'm going to plot my original relationship with LL, RR, and CC, those original values that I defined. I'm going to plot a second relationship with LL1, RR1, and CC1. The plot is going to be the same range of frequencies, the same range of horizontal and vertical axes. So those plot ranges are going to be the same. Notice that that plot expression is the same plot expression I used before, but it's embedded inside this manipulate command. And then I'm telling the manipulate command, after I close the plot command, I'm telling the manipulate command that I want CC1 to start at a value of 10 times 10 to the minus 9 farads, and then I want to be able to adjust it between 2 times 10 to the minus 9 farads and 20 times 10 to the minus 9 farads. Then I'm also giving it a value to start for LL1 and the range that I want LL1 to vary through, and I'm giving it a starting value for RR1 and the values I want to be able to vary RR1 through as well. And so again, what this manipulate command is going to allow me to do, using the second relationship in that plot command, it's going to change those values, allow me to change those values interactively and see what it does to the plot. So let's go ahead and execute this. Here is the plot that's made. I started my LL1, CC1, and RR1 with the same values LL, CC, and RR, and so the two plots are overlaid. But now you see I can use these sliders and I can see what effect changing the inductance has on this relationship. I can see what effect changing the capacitance has on the relationship, and I can see what effect changing the resistance has on the relationship. I can expand each of these parameters that I'm varying, so it'll show me what the value is for a particular shape of the curve. If I am trying to design a filter to select out a specific range of frequencies or to have specific properties, I can vary these component values until I obtain those properties, and I can then search for those components to incorporate in the circuit. So again, this manipulate command is a really, really useful tool in Mathematica for you to investigate and visualize how new relationships that you're seeing in mathematics and in physical systems, how they behave as you vary different parameters in those relationships.